Hello, it's Keith here, and this is lesson 27 of the platform-specific series of my Z80 programming tutorials. Now, over the last few weeks, we've looked at the MSX and the ZX Spectrum, and this week we're going to move on to the Enterprise. Now, the Enterprise is quite unusual. It was a major commercial failure at its time, but rather surprisingly, it's actually got some of the most powerful hardware within the Z80 range, especially when it comes to memory mapping. You may remember that the ZX Spectrum was fairly limited in its memory options. The Amstrad CPC had some good options, but still not much flexibility, and most MSXs, because they didn't have the memory mapper, were quite limited in what they could do with regards to Bankswitching. However, the Enterprise has the same functionality as the advanced MSX memory mapping that only the last generation of MSXs had, but every single Enterprise released has the advanced memory mapping capabilities like the MSX by default. So we can bankswitch any bank of 16K memory into any position within the system, and even have two banks of 16K memory pointing to the same physical bank in memory. Not only that, but the operating system can allocate and deallocate memory for us, so we can request memory from it and not have to worry about where the system memory is or how much the system has. We can just ask for memory and the system will tell us if we can have it and which piece of memory it can have. So the Enterprise is far more powerful than the other systems, but it does mean we have to kind of play nicely with the operating system. That is, if we're ever going to use the operating system. If we aren't going to use the operating system for disk operations, then we could actually just flush out all its memory, take all the banks, detect them ourselves, and do everything by ourselves. But I'm going to do things the way I did in Chibi Akuma's, and that is request the banks in a polite way from the operating system so that we can use them correctly. Now, a 64K system will have 4 banks of memory. Now, banks on the Enterprise are numerical, so they can go from 0 to FF. That's 255, of course. Low bank numbers will be ROMs, so banks 0 to 4, for example, will be ROM banks, and the high banks will be RAM. And on a 64K system, you will always have an FF, FE, FD, and FC bank of memory, and that will be the only 64K in the system. Now, on a 128K system, you'll gain an extra 8 banks, but the FF, FE, FD, and FC banks will still be the internal banks built within the system, and the extra 64K will be numbered FB, FA, F9 and F8. If you had even more memory, it would continue going down. It's quite important to notice that the basic 64K does have one special feature that the additional memory does not. That is that the 64K is the only memory that can be used for video memory. So you would want to use your FD and your FE bank for your video buffers, and use your F8, F9, FA and FB banks for other purposes. Now, when you switch on an Enterprise, 2 banks will already be allocated to special purposes. The FF bank is the system bank. This has the system variables, the stack, things like that. And the lowest numbered bank, whatever that is within the system, will be the 0 page. And this will be loaded into the lowest area of the system memory, and that will have things like the RSTs in there. Now, as I say, the FF bank is always the system page, or at least in my experience, and the 0 page will always be the lowest numbered bank within the system, whether that's F8 on a 128K system or even lower on a 256K system. So how do we request memory from the system? Now, when we want to call the Enterprise commands, we use RST6. Now, on VASM, I have to multiply it by 8 to get it to work. Some assemblers would just use RST6 as a command. WinApe did, but VASM does not. And then following the RST command, or the EXOS command as you sometimes see it, you have to put a byte, and you would put a byte 24 to request memory from the system. And what the system will do is it will attempt to get some memory, and if it succeeds, it will return the segment number, which is these kind of numbers here, in C. If it fails, it will return non-zero. If we've used the segment and we no longer need it, we can free it with command 5. So again, RST6 followed by a byte of 25. And this will free the segment in the C register. So it's very simple to give memory and to take memory from the system. There are some special cases though. If we've requested absolutely every bank of memory, remember we will get F9 followed by FA, followed by FB, followed by FC, followed by FD, followed by FE. If we've requested all of these banks, then the only remaining bank would be FF, and half of this bank would already be used. And so what would happen is it would return that, but it would return a non-zero, and then it would return the offset where the important data was in DE, so we would only be able to use up to that offset as free memory within that bank. And when it comes to freeing it, it's much easier. We just give C as the segment we want to release. So how do we actually use the segments once we've requested them from the system? Well, again, the Enterprise makes this really easy for us. There are 4 ports within the system, ports B0 to B3, and each of these handles a 16K bank of the system memory. And all we do is we add the number of the bank we want to page in to the port, and that memory area will be paged in. Of course, we'd have to be careful with the 0 range with B0 because that would affect our OSTs. But apart from that, we can bank in things wherever we want, just of course bearing in mind our stacking things. Now, with Chibi Akumas, my game, I was always using the B1 bank to emulate the Amstrad CPC because the Chibi Akumas for Enterprise was pretty much a straight port of the CPC version. And this was where the Enterprise made things really easy because it can almost entirely emulate a CPC screen, and also it can emulate far better than the CPC's Bankswitching. So it made it very easy to port the game, and that's why the Enterprise port was so quick to do. So as I've said, all we need to do is load A with the bank number we want, like F3, out it to the port that handles the memory area we want to control, and that's all we need to do. So switching memory in is very easy, and requesting memory from the system is also very easy. But as I said before, there is one limitation, which is that only these 4 banks can be used for screen memory, or the only 4 banks on a 64K system. None of the other banks on any system, no matter how much you upgrade it, can be used except for the internal 64K ones, which are wired to do the screen. So how do we get a screen bank that we can use? Well, we know that the screen banks are going to be FC or above, and so all we do is we request banks from the system, remembering the bank numbers that it gave us, and then when we get a bank number that we actually wanted, an FC or higher bank, we then release all the ones we didn't really want, because it will always allocate them consecutively. So if we request one and we get F9, we just remember that. We request another one, we get FA, we remember that. We request another one, FB, request another one. That's our real bank that we can use. And then if we wanted a second buffer, we could just request another one again. And then we just need to recall the ones that we didn't want and release them. And we can use that. We do that with a temporary buffer or push pop commands. But we just need to release the memory we didn't need. So that's how we can get our screen buffers here. And of course, we would just page them in. And with Chibi Akumas, one was paged into the B2 port and one was paged into the B3. Again, to simulate the Amstrad CPC screen buffer flipping. So again, very easy. So how are we going to detect our 64, 128K and 256K systems today? Well, let's have a look. So here's today's code, and you should recognize it already. So we're requesting segments here, and what we're going to do is we're going to keep requesting them until it fails. And every time we do, we're going to push the segment that we were allocated because we want to release them later. And then we're going to increase the accumulator here, which is going to be the count of how many banks we've got. At this point, we've requested every bank that the system can give us, and depending on how many banks we found, we will know how much memory we've got. If we were only able to request 4 extra banks, then we've got a 128K system. And the reason for this is we're already using some of the banks within our system already, because by the time we run this in my tutorial code, we will have already requested a screen buffer, and we will have requested a bank of memory for our system, and then the 0 bank and the system bank will already be in use. So there will only be 4 unused banks at the point that this code is called. If you were using it in your own code and you hadn't requested a screen buffer and hadn't allocated a bank already to the 8000 range, you would have to change this to 6. But in this example, it will work, and if it doesn't work, you would just want to run it, see how many banks were detected, and tweak the settings accordingly. So when we get to this point, we now know how many banks are free, and we're going to release the ones that we allocated that we didn't really want, because we were only allocating them to see how many there were. Of course, if we wanted to actually use them, we could enable this don't free memory function here just by unremming this line here, and that would leave them allocated so we could use them. Now, technically, if we were going to be professional about it, what we would want to do is store them somewhere in some kind of temporary variables, and you would want to put that in here somewhere rather than this push command. But you could also be a bit more aggressive and just, you know how many banks there are, so you can guess which ones are where and just use them without respecting the enterprise operating system. That's up to you. As I've said before, if you're not going to use the system firmware, you can be a bit more cheeky like that. But if you're going to expect the disk system to work for you properly later, you don't want to have risked corrupting its data. So while you can be pretty sure on a 128K system, F9 to FE will be free and available for your use, if you're going to be professional about it, you don't want to rely on that, because maybe the user's got some very strange add-ons and FE is already in use by one of those add-ons. So you should really request the banks and work out which banks you were requested, but it's up to you. Again, if you're just coding for fun, it probably doesn't matter, so I'll leave that up to you. So anyway, this is just using the DB25, popping back each of the values that we were given to release all of the banks that were allocated. Now when we get down here, we're now going to compare the accumulator, which we've restored with the value of how many banks were requested successfully. If there's 4 banks successfully requested, we're on a 128k system. If there's 12 banks requested successfully, we're on a 256k system. And so we're just increasing E here. So E will be 0 on a 64k system. It will be 1 on a 128k system. And it will be 2 on a 256k system. And here we've got the bank swapping code, which is taken straight out of Chibi Akuma's. As before, we've got a set current command, which will set the current bank. And we're always using the bank controlled by B1, which is at the 4000 range. And that's because, as I've said, this is copied straight out of Chibi Akuma's, and that's how that game worked. So set current will kind of permanently set the bank. Set will temporarily set it for things like playing the music, things in interrupts maybe. And then reset will set to the same bank that was set with the last set current command. And that's how the Chibi Akuma's game worked. You would use set current in your main game loop, but then if you needed to quickly switch in some sprites or something, you would use the set command for the temporary work and then use the reset command to put everything back the way it should be. So there you go. And you can see here there's actually some temporary variables that this code doesn't really use and should probably be taken out, but these were used to store the banks that the system successfully allocated for the extra data that Chibi Akuma's needed. So I was doing things properly because I needed the disk system to keep working for me. So as before, we're going to be using our testing program, and we're going to be doing basically the same as last time. We're going to run the get hardware version command, which will return D as 0 on the enterprise at all times, and E will be representing how much memory is in the system. And then we're going to try and switch in 3 of the custom banks, and we're going to write some bytes to those banks just to see what happens. So let's have a go. So you can see we've got 64k of memory here. So if we just do run program.com, you can see that E is 0, but unlike the other systems, we are actually able to switch in alternate memory banks because, as I said, even though the Enterprise 64K has no extra memory, we can switch any of those banks in at any position. So we have effectively switched in FF, FE and FC into the second bank in the memory range because, as I said, any bank can be in any position or in multiple positions on the Enterprise. So let's change our machine settings. And let's change to 128. And let's run our program again. So now you can see there's a 1 here. That's because we've detected 128k of memory. But again, we're able to switch in those banks wherever we want. I should say as well, this is actually screen corruption because we're writing to the screen bank while we're doing this. So obviously my testing probably should be done before you start using the screen, but we're not causing any major problems there, even though it is making a bit of a mess of our screen. But never mind. So let's configure again, and let's change up to 256. And you can see we've now detected 2 because we've detected 256k of memory. And again, we're just switching in the same banks, but we're not using any of the extra banks, so there's not too much to see there. Now, interestingly, one thing actually went wrong when I tried to test my code today. Although it worked fine on my virtual machine, which I do most of my tutorial development on, for some reason the emulator seems to be working slightly differently when I'm running it on this Windows 7 machine, because I was using D here to back up the register because I couldn't use push and pop because I was popping off values here. It was working fine before, but now it wasn't working, and that D register was actually getting corrupted. So I've changed it to IXL here, and that does seem to be working okay. Of course, the alternative would be to do something like self-modifying code and do something like this. You could do that rather than using the IXL or using any of the other registers. I'm trying to avoid using self-modifying code these days because it doesn't work well with ROM, and I'm trying to transfer my code between different systems to do the same job to save time and make my code generally better commented and more reliable. But as I say, in this case, I'm now using IXL, but when I showed it you earlier, I was using, I think it was D. So I just wanted to tell you that while what was there was tested before. It doesn't seem to be working now on this emulator, so for some reason it seems to be slightly configured differently on my Windows 7 machine. Anyway, that's all for today's lesson. Next week we're going to look at another system. We're going to be looking at the SAM Coupe. The SAM Coupe is a system with an incredible amount of memory. There are two versions of the SAM Coupe. One has 256k, the other has 512, and it can even go up to 4 megabytes, I believe. However, that said, it does have some unique problems on the SAM Coupe, so we're going to look at that next week. Anyway, I hope you've enjoyed this week. Thanks for watching and goodbye.